Cold War and Beyond. Military engineers. Cold War and beyond, military engineers designed machines that defied imagination, nuclear-powered missiles that could poison the sky, rockets the size of skyscrapers, armed space stations orbiting above Earth. On paper, they promised dominance. In reality, they threatened escalation, catastrophe, or consequences no one could fully control. From doomsday torpedoes to bomb-powered spaceships, these projects pushed strategy to its breaking point. This is the story of 14 military programs that went too far, so extreme, so destabilizing, or so politically explosive that even the nations building them decided to pull the plug. Project Pluto, the nuclear-powered doomsday missile. In the late 1950s, as intercontinental ballistic missiles reshaped nuclear strategy, a quieter and far more unsettling concept was being tested in the Nevada desert. It was called Project Pluto, and it proposed something that pushed deterrence logic to its absolute edge: a cruise missile powered not by conventional fuel, but by an unshielded nuclear reactor. The underlying engine, known as the Supersonic Low-Altitude Missile, SLAM, relied on a nuclear ramjet. Air entering the missile at supersonic speed would pass directly through a reactor core, where extreme heat would supercharge the airflow and produce thrust. No shielding protected the reactor because shielding would make the missile too heavy. Instead, the design accepted a chilling premise: the exhaust would be radioactive. This was not a weapon designed for a single strike. The concept envisioned a missile that could fly at low altitude across continents, evading radar, carrying multiple hydrogen bombs, and loitering for extended periods before delivering its payloads. Even before detonation, it would contaminate the environment beneath its flight path with radioactive exhaust. In effect, the missile itself functioned as a roaming source of nuclear pollution. Testing focused on the reactor, not the full missile. Engineers successfully ran the Torrey 2A and Torrey 2C reactors at full power inside a specially constructed facility in Nevada. The technology worked. The reactor produced immense heat and sustained output, proving that nuclear ramjet propulsion was technically feasible. The barrier was not physics, it was a consequence. Strategists began to question what deploying such a weapon would mean politically and environmentally. A missile that sprayed radiation over neutral or allied territory during transit risked international backlash even before war began. If it crashed accidentally, the reactor would scatter nuclear material unpredictably. Unlike ballistic missiles, which completed their flight in minutes, SLAM would travel for hours at treetop height, making its presence both terrifying and destabilizing. By the mid-1960s, advances in ICBMs and submarine-launched ballistic missiles made Project Pluto strategically redundant. More importantly, its sheer extremity made it politically radioactive. The program was canceled in 1964. Project Pluto demonstrated that nuclear propulsion could power a missile indefinitely. It also demonstrated that some weapons, even if technically possible, were too extreme to deploy without reshaping the very world they were meant to defend. Project A-119, nuking the moon. At the height of Cold War anxiety, symbolism mattered as much as hardware. In 1958, as the Soviet Union celebrated early space milestones, the United States quietly studied a proposal that would have transformed the moon into a geopolitical stage. The study, later revealed as Project A-119, examined the feasibility of detonating a nuclear device on the lunar surface. The rationale was not military in the conventional sense. There was no battlefield advantage to be gained on the moon. Instead, the objective was psychological shock. A nuclear explosion visible from Earth, timed and photographed for maximum impact, would demonstrate American technological reach and nuclear superiority. In the early space race, where prestige translated into political leverage, such a spectacle was considered a potential strategic message. Scientists were tasked with determining whether the explosion would be visible to the naked eye and what kind of dust plume it might create in the moon's low-gravity environment. The proposal included careful calculations about yield, detonation altitude, and photographic documentation. Ironically, respected astronomers were consulted to assess the scientific value of the data that might result from the blast, including information about lunar composition. Yet, even within the defense establishment, the idea triggered unease. A nuclear detonation in space risked contaminating future exploration and could undermine emerging norms about peaceful use of outer space. The possibility of miscalculation, either technical failure or diplomatic backlash, loomed large. If the mission failed publicly, the embarrassment could outweigh any intended show of strength. There were also moral and reputational concerns. Turning a celestial body into a platform for nuclear theatrics risked portraying space exploration as an extension of atomic brinkmanship rather than scientific advancement. As the U.S. civilian space program began to take shape under NASA, the contrast between exploration and detonation became sharper. Ultimately, Project A-119 never advanced beyond study phase. The risks to diplomacy, to scientific credibility, and to the fragile narrative of space as a frontier for humanity rather than warfare proved too great. The moon remained unscarred by nuclear demonstration, and one of the most extreme ideas of the Cold War quietly faded into classified archives. Project Orion, the nuclear bomb-powered spaceship. In the late 1950s, while chemical rockets struggled with payload limits and range constraints, a group of physicists and engineers began outlining a propulsion concept that defied conventional aerospace thinking. Known as Project Orion, the proposal envisioned a spacecraft propelled not by steady combustion, but by a controlled sequence of nuclear explosions detonated behind it. The mechanics were brutally simple. Small nuclear charges would be ejected from the rear of the spacecraft and detonated at precise intervals. A massive steel pusher plate attached to shock absorbers would absorb the blast impulse, converting explosive force into forward momentum. Each detonation would function as a pulse of thrust. Instead of fighting gravity with chemical fuel limitations, Orion would leap forward on repeated nuclear shock waves. The theoretical performance was extraordinary. Designers calculated that Orion could carry payloads measured in thousands of tons, potentially enabling crewed missions to Mars or even Saturn within a single generation. Unlike conventional rockets that required massive staging and delicate fuel balancing, Orion scaled upward efficiently. Larger spacecraft simply required proportionally larger pulses. The design suggested that deep space colonization might be technically achievable decades earlier than anticipated. But the elegance of the math collided with geopolitical reality. Every launch from Earth would require detonating dozens, possibly hundreds of nuclear devices in the atmosphere before reaching space. Even if the individual yields were relatively small, cumulative fallout would be unavoidable. The environmental implications were severe, especially after growing awareness of radioactive contamination from atmospheric testing. The signing of the Partial Test Ban Treaty in 1963, which prohibited nuclear explosions in the atmosphere and outer space, struck directly at Orion's foundation. There were also strategic concerns. A spacecraft capable of deploying nuclear devices as propulsion units could easily be interpreted as a weapons platform. Its sheer mass and potential range raised questions about militarization of space. The line between exploration and orbital deterrence blurred uncomfortably. Despite promising engineering studies and scale models, Project Orion never advanced beyond experimental design. It demonstrated that physics did not forbid nuclear pulse propulsion. What ultimately grounded it was not feasibility, but the realization that turning nuclear detonations into routine transportation would reshape environmental and diplomatic boundaries in ways the world was not prepared to accept. Soviet T-15 torpedo, the tsunami nuclear torpedo. At the dawn of the nuclear age, before intercontinental missiles could reliably span oceans, Soviet planners considered a weapon that bypassed airspace entirely. Hidden beneath the surface, carried by submarine, it would approach enemy shores undetected and unleash destruction on a scale rarely contemplated outside theoretical war rooms. This was the concept behind the Soviet T-15 torpedo, a thermonuclear torpedo so large it redefined what a naval weapon could be. The T-15 was engineered around a single overwhelming idea. If a nuclear device detonated offshore near a major coastal city, the blast and resulting water displacement could devastate infrastructure across vast areas. Early discussions envisioned multi-megaton yields. Rather than targeting warships at sea, the torpedo's mission would be strategic. crippling ports, naval bases, and industrial centers in one strike. In theory, a submerged launch platform could bypass early warning systems and deliver nuclear force from beneath the horizon. The engineering implications were staggering. At over 20 meters long and weighing roughly 40 tons, the T-15 dwarfed conventional torpedoes. It was so large that submarines designed to carry it would dedicate most of their internal space to a single weapon. That decision introduced operational fragility. A submarine, armed with only one enormous torpedo, sacrificed tactical flexibility. If the mission failed, or if interception occurred before launch, the vessel would have little alternative capability. Naval leadership quickly recognized the risks. Approaching an enemy coastline close enough to detonate a weapon of that magnitude required penetrating heavily defended waters. Anti-submarine patrols, sonar nets, and coastal defenses reduced the likelihood of success. Moreover, improvements in ballistic missile technology began offering a more reliable, faster means of delivering nuclear warheads without exposing submarines to near-certain retaliation. There were broader strategic concerns as well. A detonation designed to generate massive coastal destruction blurred distinctions between military and civilian targets. The concept leaned heavily toward total urban annihilation, raising escalation questions even within Cold War logic. As missile-based deterrence matured, the T-15 appeared increasingly redundant and disproportionately extreme. By the mid-1950s, the program was shelved in favor of smaller, more versatile nuclear torpedoes and emerging submarine-launched ballistic missiles. The T-15 remains a stark example of early nuclear-era thinking, when strategic imagination briefly embraced the idea of turning entire coastlines into targets from beneath the sea. Convair NB-36H, the nuclear bomber. At the height of Cold War anxiety, the question was not simply how to deliver nuclear weapons, but how to keep bombers airborne long enough to guarantee retaliation. Before reliable intercontinental ballistic missiles dominated strategy, endurance was everything. One radical answer took shape in the form of the Convair NB-36H, a prototype aircraft that actually carried a functioning nuclear reactor inside its fuselage. The NB-36H was derived from the massive B-36 Peacemaker bomber, already one of the largest aircraft ever built. Engineers installed a compact nuclear reactor in the rear bomb bay, heavily shielded to protect the crew compartment at the front. The concept being explored was straightforward but extreme. If a bomber could be powered by nuclear energy, it could theoretically remain airborne for days or even weeks without refueling. However, the NB-36H was not fully nuclear-powered. The reactor did not drive the engines directly. Instead, it served as a flying laboratory to test shielding, heat management, and radiation containment in flight. Even in this experimental configuration, the risks were profound. A crash involving a nuclear reactor, even one not connected to propulsion, would scatter radioactive material across whatever terrain lay below. Each test flight required escort aircraft and carefully planned routes to minimize population exposure. Shielding presented a nearly unsolvable trade-off. Protecting the crew from radiation required tons of lead and specialized materials, dramatically increasing aircraft weight. Reducing shielding reduced safety. Engineers struggled to balance survivability, payload, and performance. Meanwhile, the broader Atomic Energy Commission explored parallel concepts for fully nuclear-powered bombers, envisioning fleets that could circle indefinitely as airborne deterrents. Public awareness of radioactive fallout from atmospheric testing was rising during this period. Environmental concerns, combined with the accelerating development of ballistic missiles, undermined the bomber's strategic rationale. Intercontinental missiles could deliver warheads faster and without risking crew lives in prolonged airborne patrols. The prospect of nuclear-powered aircraft routinely crossing global airspace began to look less like deterrence and more like liability. By 1957, the program was terminated. The NB-36H had logged dozens of test flights, proving that a reactor could operate safely in the air under controlled conditions. What it also demonstrated was the immense complexity and political risk of integrating nuclear propulsion into routine aviation. The nuclear bomber never advanced beyond experimentation, leaving behind one of the most ambitious and unsettling chapters in aerospace history. Lockheed CL-1201, the flying aircraft carrier. In the late 1960s, when Cold War engineering ambition often stretched beyond conventional limits, Lockheed engineers sketched out a concept so vast it blurred the line between aircraft and airborne fortress. Known as the Lockheed CL-1201, the proposal envisioned a nuclear-powered aircraft with a wingspan approaching 1,100 feet, larger than many naval vessels, and the capacity to remain airborne for weeks. The CL-1201 was not designed as a conventional bomber. It was conceived as a flying aircraft carrier, capable of launching and recovering smaller parasite fighters mid-air. The central platform would loiter at high altitude, acting as a mobile command base and strategic presence platform. Powered by multiple nuclear reactors driving massive turbofans, it promised virtually unlimited range and endurance, constrained only by crew rotation and maintenance cycles. On paper, the capabilities were staggering. Payload projections reached into thousands of tons. The aircraft could carry dozens of interceptors, missiles, and electronic warfare systems. Its size would allow for layered defensive systems, potentially making it nearly untouchable in contested airspace. In theory, a CL-1201 could patrol above hostile territory indefinitely, projecting power without reliance on ground bases vulnerable to missile strikes. Yet, scaling aircraft to that magnitude introduced structural and aerodynamic challenges that bordered on the speculative. Wing loading, material fatigue, and the stress of turbulence on such a vast airframe raised unresolved engineering questions. The logistics of constructing runways or launch systems capable of handling an aircraft of that size were equally daunting. Even if airborne operations proved feasible, landing and maintenance would require unprecedented infrastructure. The nuclear propulsion component compounded controversy. Like earlier nuclear-powered aircraft concepts, shielding posed severe weight penalties. A crash involving multiple onboard reactors would be catastrophic, and the political consequences of routine nuclear-powered overflights across international airspace were difficult to predict. Environmental concerns, already heightened by nuclear testing debates, cast a shadow over the concept. Strategically, the project also risked obsolescence before completion. Advancements in intercontinental ballistic missiles, satellite reconnaissance, and long-range cruise missiles reduced reliance on manned airborne platforms for continuous deterrence. The CL-1201 promised dominance through scale, but scale itself became its liability, financially, technologically, and politically. Lockheed's design never moved beyond advanced conceptual study. The flying aircraft carrier remains one of the most extreme aerospace proposals of the Cold War, a vision of airborne power projection so ambitious that reality ultimately grounded it before construction ever began. Project Habakkuk, the ice warship. During the darkest years of the Second World War, when German U-boats were strangling Allied shipping lanes in the Atlantic, desperation gave rise to ideas that bordered on the surreal. One of the most unconventional was Project Habakkuk, a plan to build a massive aircraft carrier not from steel, but from reinforced ice. The problem facing Britain was strategic geography. Conventional aircraft carriers were expensive and vulnerable, and there were not enough of them to provide continuous air cover across the vast Atlantic convoy routes. Without air support, merchant ships were easy prey for submarines. The solution proposed by inventor Geoffrey Pike was startling in its simplicity. Create floating airfields from pikecrete, a composite of ice and wood pulp that was stronger and slower to melt than natural ice. Enormous floating platform, hundreds of enormous floating platform, hundreds of meters long and dozens thick, could be constructed in cold waters and used as an unsinkable aircraft carrier. Its sheer mass would make torpedo damage less decisive, and its materials were far cheaper than steel, a critical advantage during wartime shortages. Yet, practicality quickly challenged imagination. To prevent melting, the structure required an extensive refrigeration system embedded throughout its interior. That system demanded energy, infrastructure, and engineering complexity that rivaled conventional shipbuilding. Construction timelines also proved problematic. Building such a vessel in remote, cold environments would take longer than anticipated, while the war's pace accelerated. There were additional operational concerns. Maneuvering a structure of such scale, even if technically afloat, raised questions about propulsion and steering. Unlike steel ships, ice-based hulls could not easily be repaired under combat conditions. The project also faced skepticism from naval leadership, who questioned whether the experimental platform could withstand sustained operational stress in open ocean conditions. As conventional carrier production improved and long-range aircraft capabilities expanded, the urgency behind Habakkuk diminished. By 1943, the project was quietly abandoned. Project Habakkuk remains a striking example of wartime innovation driven by necessity, an audacious attempt to weaponize the environment itself. Its cancellation reflected the limits of improvisation, where bold imagination collided with engineering reality and shifting strategic priorities. Project Sundial, the doomsday bomb. In the early 1950s, as thermonuclear research accelerated, some American physicists briefly explored a concept so vast that it redefined the upper limits of destructive capability. Known as Project Sundial, it was not a weapon designed for battlefield utility or even conventional strategic deterrence. It was an exploration of scale, how large a thermonuclear device could theoretically become. The idea emerged from theoretical work at Los Alamos during the development of early hydrogen bombs. Scientists calculated that by staging fusion reactions in cascading layers, explosive yield could increase dramatically. Sundial was envisioned as a multi-gigaton device, potentially thousands of times more powerful than the atomic bombs dropped during World War II. At that magnitude, the detonation would not simply destroy a city, it could devastate entire regions. The purpose of such analysis was partly academic. Physicists sought to understand the boundaries of thermonuclear physics, how fusion reactions propagated, and what practical constraints limited yield. Yet, the strategic implications were unmistakable. A weapon measured in gigatons would not discriminate between military and civilian targets. It would represent annihilation at continental scale. Even within Cold War deterrence logic, Sundial raised uncomfortable questions. Deterrence theory relied on the threat of unacceptable damage to prevent aggression. But at gigaton yields, destruction risked becoming indiscriminate to the point of mutual extinction. There was also the environmental dimension. Atmospheric testing had already demonstrated global fallout effects from far smaller weapons. A Sundial-scale detonation could inject massive quantities of radioactive debris into the stratosphere, with unpredictable climatic consequences. As thermonuclear weapon design matured, attention shifted toward deliverable warheads with optimized efficiency, rather than maximal theoretical yield. Practical constraints, missile payload capacity, strategic targeting doctrine, and geopolitical optics favored smaller, more precise devices. The largest weapon ever tested, the Soviet Tsar Bomba, reached 50 megatons, but even that was scaled down from its theoretical maximum for safety and political reasons. Project Sundial never progressed beyond conceptual study. It remains a reminder that during the early hydrogen bomb era, the question was not whether greater destruction was possible, but whether it was survivable, even for the nation deploying it. Some thresholds were technically reachable, yet strategically indefensible. Boeing YAL-1, the airborne laser 747. In the early 2000s, amid growing concerns about ballistic missile proliferation, the United States pursued a concept that seemed pulled from science fiction: destroying enemy missiles with a high-energy laser fired from a modified jumbo jet. The platform chosen was a heavily altered Boeing 747, and the program became known as the Boeing YAL-1. Could deposit enough energy onto the missile's skin during this window, it could cause structural failure or detonation before the warhead separated. An aircraft operating near hostile airspace would track the launch in real time, focus its beam, and neutralize the threat within seconds. Technologically, the challenge was enormous. The YAL-1 carried a megawatt-class chemical oxygen iodine laser housed in its fuselage, along with advanced tracking and beam control systems. A large turret mounted in the aircraft's nose directed the laser toward its target. Engineers had to compensate for atmospheric distortion, turbulence, and the aircraft's own motion to maintain a steady beam on a rapidly ascending missile. In 2010, the system achieved a milestone by successfully destroying a test ballistic missile during boost phase. The demonstration proved that airborne laser interception was technically possible. However, operational viability proved far more complicated. The aircraft would need to loiter relatively close to enemy launch sites, placing it within range of advanced air defenses. Chemical laser systems required substantial onboard consumables, limiting sustained firing capacity. Each shot consumed specialized fuel, making repeated engagements logistically demanding. Moreover, the cost of development ballooned into billions of dollars, raising questions about scalability. Strategically, the system's vulnerability became a focal concern. A large 747 operating near hostile territory would be a high-value target. As missile defense alternatives such as ground-based interceptors and space-based sensors advanced, the YAL-1's niche narrowed. Critics argued that the platform was technologically impressive but operationally impractical. By 2011, the program was canceled. The YAL-1 never entered active service, leaving behind a legacy of technical breakthroughs overshadowed by cost and survivability concerns. It demonstrated that directed energy missile defense was achievable in principle, but perhaps too extreme in scale and expense for routine deployment. DARPA Falcon HTV-2 Mach 20 Global Strike. At the height of post-Cold War military innovation, speed became the new frontier. The objective was not larger bombs or heavier platforms, but time compression, striking anywhere on Earth within an hour. That ambition crystallized in the DARPA Falcon HTV-2, an experimental vehicle designed to travel at speeds approaching Mach 20. The concept behind the hypersonic technology Vehicle 2 was deceptively simple. Launch a glider atop a conventional rocket, release it at high altitude, and allow it to skim the upper atmosphere at extreme velocity toward its target. Unlike ballistic missiles, which follow predictable arcs, a hypersonic glide vehicle could maneuver laterally, complicating interception. In theory, this would create a conventional global strike capability, delivering non-nuclear payloads with near-nuclear response time. Physics, however, proved unforgiving. At Mach 20, aerodynamic heating becomes a dominant factor. The HTV-2 would encounter temperatures exceeding 3,500 degrees Fahrenheit as it sliced through the atmosphere. Designing materials capable of withstanding such heat while maintaining structural integrity posed immense challenges. Even small instabilities in airflow at hypersonic speeds could cascade into loss of control within seconds. 2 flight tests were conducted in 2010 and 2011. In both cases, the vehicle successfully separated from its launch booster and reached hypersonic velocity. Within minutes, telemetry indicated aerodynamic instability and loss of control. Safety protocols triggered termination sequences, sending the vehicle into the ocean, while the brief flights confirmed that sustained hypersonic glide was achievable for short periods. They also exposed how narrow the margin for control remained at such speeds. Strategically, the project stirred debate. A weapon capable of striking globally within an hour, even without nuclear warheads, could be misinterpreted by adversaries as a nuclear launch. The compressed decision time risked escalation through miscalculation. Additionally, the cost of research and repeated testing failures fueled skepticism about feasibility. The Falcon HTV-2 program was eventually discontinued, though hypersonic research continues in various forms. It represented a leap into the edge of atmospheric physics, where engineering ambition met thermal limits and geopolitical uncertainty. Mach 20 was reachable, but controlling it consistently proved far more extreme than initial projections suggested. McDonnell XF-85 Goblin, the bomber-launched fighter. In the late 1940s, before aerial refueling became reliable and before long-range escort fighters matured, the U.S. Air Force faced a strategic dilemma. Strategic bombers such as the B-36 could reach deep into enemy territory, but once there, they would be alone. Conventional fighters lacked the range to escort them across continents. The proposed solution was unconventional and daring: carry a fighter inside the bomber itself. That idea materialized as the McDonnell XF-85 Goblin. The Goblin was tiny by design, just large enough to house a pilot, a jet engine, and 4 machine guns. It would be stored inside the bomber's bomb bay and deployed mid-air when enemy interceptors approached. After combat, the fighter would dock with the bomber using a retractable trapeze mechanism, latch onto a hook above its nose, and be pulled back inside. On paper, the system promised self-contained defense. A bomber group could carry its own escort fighters without relying on distant air bases. In practice, the concept collided with aerodynamic reality. Docking mid-air proved extraordinarily difficult. Turbulence generated by the bomber's massive airframe created unstable airflow around the trapeze area. During early test flights in 1948, Goblin pilots struggled to align the small jet with the docking hook. Even minor misjudgments caused the fighter to swing violently, risking collision with the bomber's fuselage. On one occasion, the Goblin struck the trapeze and cracked its canopy, forcing an emergency landing. The XF-85's limited fuel capacity also constrained its usefulness. Designed for short engagements, it lacked endurance for extended combat or diversion to distant airfields. If docking failed, the pilot had minimal options. The system required precise coordination under ideal conditions unlikely to exist during hostile interception. Meanwhile, aerial refueling technology was advancing rapidly. Fighters equipped with refueling probes could now accompany bombers across intercontinental distances without the complexity of parasite deployment. Compared to tanker-supported escorts, the Goblin appeared mechanically fragile and operationally risky. The program was canceled after only 2 prototypes were built and tested. The XF-85 Goblin remains one of the most imaginative solutions ever proposed to the escort problem. A compact guardian designed to emerge from a bomber's belly. Its failure underscored a recurring lesson in military innovation. Ingenuity alone cannot overcome the chaotic physics of combat airspace. Avro Canada CF-105 Arrow, the cancelled Super Interceptor. In the 1950s, as Cold War tensions intensified and long-range Soviet bombers were perceived as a direct threat to North America, Canada embarked on one of the most ambitious aerospace projects in its history. The result was the Avro Canada CF-105 Arrow, a sleek, delta-wing interceptor designed to fly at speeds exceeding Mach 2 and operate at altitudes above 50,000 feet. The Arrow was conceived as a high-speed guardian of Canadian airspace, capable of intercepting incoming bombers long before they reached major cities. It featured advanced avionics, a sophisticated fire control system, and internal weapons bays designed to carry guided missiles. For its time, it was technologically ahead of many contemporaries. Early test flights demonstrated impressive performance, reinforcing national pride in Canada's aerospace industry. Yet the project's ambition collided with shifting strategic realities. As the Arrow advanced toward operational deployment, the threat landscape began to change. Intercontinental ballistic missiles were emerging as the primary nuclear delivery system, reducing the emphasis on manned bomber interception. Simultaneously, the program's costs escalated dramatically. Developing cutting-edge engines, avionics, and airframes required sustained financial commitment, and critics questioned whether Canada could justify such expense independently. Political tensions intensified around procurement decisions. The government faced pressure to integrate more closely with American defense systems, including missile-based continental air defense networks. Investing heavily in a domestically produced interceptor risked duplication of capabilities that Allied systems might provide more economically. Debate shifted from engineering achievement to fiscal responsibility and alliance alignment. In February 1959, the Canadian government abruptly canceled the program. Completed aircraft were scrapped, and production lines were dismantled. Thousands of engineers and skilled workers lost their jobs. many eventually relocating to the United States and contributing to projects such as NASA's space program. The CF-105 Arrow's cancellation remains controversial in Canada. To some, it symbolizes lost industrial independence and technological potential. To others, it reflects pragmatic adaptation to evolving strategic conditions. What is clear is that the Arrow was not canceled because it failed technically. It was canceled because its ambition, financially, politically, and strategically, proved too extreme for the moment in which it existed. Sea Dragon rocket, the ocean-launched mega rocket. In the early 1960s, as the space race intensified and rocket engineers pushed toward heavier payloads, one proposal took scale to an unprecedented extreme. Known simply as Sea Dragon rocket, it was conceived as the largest rocket ever designed, so large that it would not launch from a traditional pad, but from the ocean itself. The concept emerged from engineers at Aerojet, who sought to simplify rocket construction rather than refine it. Instead of precision-crafted components built in sterile facilities, Sea Dragon would use thick steel walls, simple pressure-fed engines, and shipyard manufacturing techniques. The first stage alone would stand roughly 500 feet tall and measure 75 feet in diameter, dwarfing even the Saturn V. Payload projections exceeded 500 tons to low Earth orbit, an order of magnitude beyond most operational launch vehicles of the era. Its launch method was as radical as its size. The rocket would be constructed in coastal shipyards, towed horizontally to open water, then raised vertically using ballast tanks before ignition. Ocean launch eliminated the need for massive, fixed infrastructure and allowed flexibility in selecting launch coordinates. The sea would absorb acoustic shock and reduce structural stress from exhaust reflection. On paper, the simplicity offered cost advantages. Heavy steel construction reduced reliance on exotic alloys, and pressure-fed engines eliminated complex turbopumps. Yet, practical challenges mounted quickly. Handling, transporting, and stabilizing a rocket of that size in open ocean conditions required extraordinary precision. Sea states, weather variability, and maritime logistics introduced risks not present at fixed launch sites. There were strategic concerns as well. A rocket capable of lifting such enormous payloads had clear military implications, particularly for deploying large reconnaissance platforms or potentially weaponized space systems. As Cold War tensions shaped space policy, the optics of an ocean-launched super rocket blurred civilian exploration with strategic projection. Ultimately, the program remained conceptual. NASA prioritized more immediately feasible launch vehicles, and funding shifted toward Apollo and other operational programs. Sea Dragon never moved beyond design studies. It remains a striking example of Cold War ambition, an attempt to bypass traditional engineering constraints through brute scale and maritime innovation. Its cancellation reflected not technical impossibility, but the reality that even in the space race, some leaps were simply too extreme to fund, field, or control. Soviet Almaz Space Station, the armed space station. At the height of Cold War rivalry, space was no longer viewed solely as a domain for exploration. It was increasingly seen as a potential high ground for surveillance and strategic advantage. Within that mindset, the Soviet Union developed Soviet Almaz Space Station, a classified orbital platform designed not for scientific research, but for military reconnaissance. Almaz stations were intended to host crews who would operate high-resolution optical cameras capable of photographing military targets across vast swaths of Earth. Unlike automated satellites, a manned station allowed real-time decision-making, flexible targeting, and film retrieval. In theory, this human presence in orbit could adapt more quickly than ground-controlled reconnaissance systems. What made Almaz extreme, however, was not just its surveillance mission, it was its armament. At least one Almaz station was equipped with a modified 23mm autocannon, reportedly adapted from an aircraft gun. The weapon was intended as a defensive measure against hostile satellites or potential space-based threats. Firing a cannon in orbit introduced extraordinary engineering challenges. Recoil management in microgravity required precise calculations, as even small momentum shifts could alter the station's trajectory. The concept of orbital gunfire marked a dramatic escalation in the militarization of space. We're rapidly improving, reducing the we're rapidly improving, reducing the necessity of human presence. Film return capsules and electronic transmission capabilities evolved, offering intelligence collection without the logistical burden of sustaining astronauts in orbit. There were also diplomatic considerations. The Outer Space Treaty of 1967 prohibited weapons of mass destruction in orbit, but conventional weapons occupied a gray area. An armed space station risked triggering reciprocal militarization by other powers, intensifying an already fragile strategic balance. Several Almaz stations were launched under civilian salute designations to obscure their military purpose. Over time, however, the program lost momentum as unmanned reconnaissance satellites proved more efficient and less politically provocative. The Almaz project revealed how far Cold War strategy was willing to extend into orbit. It demonstrated that even space, once imagined as humanity's shared frontier, could become a potential battleground. Ultimately, the cost, complexity, and escalation risk of maintaining an armed outpost in orbit rendered the concept too extreme for long-term deployment.